Today's talk is about analog and hybrid computing, something you might have heard already, but maybe have never heard about. You are studying computer science, so all you think about is digital computers, or to be more precise, stored program digital computers. All what we as computer scientists do is think about algorithms and think about how to speed up things, how to process data in ever larger dimensions. And all we do on things we take for granted, take for given on stored program digital computers. Interestingly, digital computers are not the first idea that came into the world when people started to think about how to compute by machines. There were other approaches long before digital computers, which are today known as analog computers. And I will talk, of course, more about this specific niche of computing, but there's another paradigm of computing which you all have at least heard about, and that is quantum computing. Yeah, die kommen sofort. Sorry. Maybe I should already start sharing my slides, but I thought I'd wait a moment. Okay. You only see the introductory slide at the moment. And there's another paradigm of computing which you all have heard about, and that's quantum computing. And quantum computing and analog computing are pretty similar, in fact. Their most striking similarity is that they are completely different from a stored program digital computer. So let's directly dive in and have a look what the heck is an analog computer and why should we care about analog computing, and why maybe what are problems of digital computers. Nowadays, digital computers are ubiquitous. You have digital computers everywhere. You have them in every single controller and light switches, in cars, in really everything, in your mobile devices, in wearable computing devices. Wherever you look, you are surrounded by digital computers. Digital computing has really taken over the world. But digital computing has some basic problems which we as computer scientists have to overcome in the near future. The main problem is they exhibit a rather large power consumption. If you have a look at the current server CPU, for example, you will see that they have so-called TDPs, thermal design powers, of about 250 watts. That's an incredible amount of heat that is exhibited by a modern computer, by a modern processor unit. And that is one of the reasons why we cannot just increase clock frequency more and more. If you have a look at the development of clock frequencies during the last maybe 10 or even 20 years, you will realize that clock frequencies have not increased at all, basically. About half a year ago, I found, while rummaging through storage at home, I found an old laptop from which I owned in 2000. And this old laptop already had a CPU clock frequency of 3 gigahertz. That's about the same clock frequency my current laptop shows. And of course, my current laptop is significantly faster, but it's faster due to architecturally tricks which have been implemented in the CPU. There are more arithmetic logic units. There are more clever algorithms for instruction rescheduling and the like, but the basic clock frequency has not increased considerably during the last 20 years. And there's a reason for this. There's a couple of reasons for this. The first reason is that power consumption increases more than linear. To be more exact, it increases about quadratically with clock frequency. So if we double the clock frequency of a given architecture, you can basically expect a power consumption which is about 4 times higher than it was before. That's a real problem. If you have a CPU which already exhibits 250 watts of electrical power, you would have a CPU which where you have to get rid of 1 kilowatt of excess heat, and that's just not possible. Of course, you could argue, okay, we need more clever, more complex cooling systems. And this idea is not new either. If you have a look back in the history of computing, you will find the machines designed by Seymour Cray and his colleagues. And they used, for example, Freon as a cooling agent in the early Cray machines. And Cray 2, for example, had such a high heat density that the overall computer system was just sitting in a bath of Freon under pressure to get rid of the excess heat. So no, implementing better cooling is not the right direction to go. Another problem is we cannot really shrink on-chip structures much further. We now see chips with structure sizes of about 7 nanometers, which is in itself more than impressive. I'm still puzzled by how they manage to project these structures on the chip with extreme ultraviolet light and the like, and really etch away the unnecessary parts of a silicon chip. That's really impressive at this structural size of a couple of nanometers. But when you are thinking in structure sizes of 7 nanometers, there is not much to shrink anymore. An atom has a finite size, and you need at least a couple of atoms to build an isolator or build a transistor. Okay, there were papers which proposed transistors based on single atoms, but even if you have a transistor based on a single atom, that's it. You cannot shrink it further down. So we cannot increase the clock frequency much higher. We cannot shrink our parts on the chips more, and there is still a third real problem lurking behind the corner, and that's Amdahl's law. If you have ever programmed a massively parallel or vectorized computer, you have already realized that Amdahl's law can really make your day a bad day, since you always have some non-parallelizable code in an algorithm, and this basically sequential code slows down your speed up, which can be achieved by parallel processing. So throwing more and more CPUs on a single problem does not really solve the problem. And the next point is, if you have a look at a modern CPU chip, what you see is a couple of arithmetic logic units, maybe 3 or 4 or 5. And lots of transistors devoted to cache memory, lots of transistors devoted to control structures. You need out-of-order execution. You need things like branch prediction. You need things like speculative execution. And if you lean back and think about it for a moment, you will realize most of the transistors on a modern CPU of a digital computer are not directly involved with the actual computation. Their sole purpose is to bring data to the arithmetic logic units and to retrieve data from the arithmetic logic units. So we have about maybe 80% or 70% of our chip area, which is packed with transistors which do not actually perform computations. And that is really strange, to be honest. Have a look here. If you think supercomputer, you will most probably think of an installation like this. And these installations are really impressive. At the beginning of this year in February, I was invited to visit the computer center at CERN, and it was really mind-blowing to see the vast computer installations at CERN. But there was another thing that was also blowing, and that was fans and cooling systems. It is incredible how much energy such a supercomputer really needs to run. And the next slide, that is not a joke. It looks like something from the Guinness Book of Records from plumbers. That is these are the preparations for the cooling system of a supercomputer. And honestly, that is not the right direction to go. We cannot afford to use more and more power to power more and more CPUs to solve problems which do not really benefit linearly from a speed up given by multiple CPUs. So we need some different paradigm to do computing, high performance computing, for example. And this slide is pretty well known in CPU circles, power density. if you have a look back at the early days of home computing, for example, the early 1980s, with machines like the Commodore 64 or a Sinclair ZX81 or a ZX Spectrum, you will realize that these machines did not need any cooling at all. Why? Because the clock frequency was so low. A Z80 processor with 4 megahertz of clock frequency requires maybe half watt or 1 watt, but not substantial amounts of power. Nowadays, we have already reached power densities which rival, for example, a nuclear power plant. If you have a look at an actual CPU chip, you will see that the chip is basically two-dimensional. That's not much of a volume, such a chip. So you only have a surface to transfer heat through. And the surface of the actual CPU chip is maybe 2 by 2 centimeters, 4 square centimeters. Now imagine how complicated it is to get rid of 250 watts of excess heat from an area of only 4 square centimeters. That's a real problem. Let's have a look at some actual computer systems. I have to admit there's already a new top 500 list out, but I didn't find time to update these slides. So that's a couple of weeks old, a couple of months old, to be honest, this slide. But a couple of months ago, the fastest digital supercomputer was Summit at the Oak Ridge National Laboratory. And this machine has a whopping 148.6 petaflops, with about 2.5 million cores and requires about 10 megawatts of electrical energy to run. That's about 1.5 gigaflops per watt of power invested in this computing system. There's another list. You may have heard of the top 500 list. This list is published twice a year and lists the 500 fastest supercomputers in the world. And nowadays, there's another list, the Green 500 list, which is not up to date, as I have realized. But the last system listed in the Green 500 list was the MN3 system in Japan, which exhibits only 1.6 petaflops with 2,080 cores and only consumes 77 kilowatts. That's about 21 gigaflops per watt. That's substantially better than the Summit system in Oak Ridge. But every one of us carries around a really interesting computer, namely the human brain. The human brain exhibits a computational power of about 38 petaflops. So it's about a fourth of what the Summit system at Oak Ridge can do. But a human brain runs on about 20 to 25, depending on who you are asking, 20 to 25 watts of power. That is really remarkable. And looking at biological systems makes it clear that nothing in nature works by executing an algorithm. To state it quite bluntly, the idea of a stored program digital computer is brilliant, one of the most brilliant ideas ever, but it's a strange idea since it really has nothing to compare in nature. Nothing in nature can afford so much energy for computation, so nature has to go another direction. If you have to live from what you eat, your power budget is not that high. Have a look at an extreme athlete or something like that. People like these can perform work of a couple hundred watts for a limited amount of time, but that's all that you can do with a biological system. So in order to implement immense amounts of computing power, nature had to go a different way. And your brain is certainly not a digital computer. That's not to say that digital computers will never be able to exhibit something like consciousness or the like. I'm personally convinced that machines can, of course, be conscious, but that's something for a different talk. But our current digital computers have much too high power consumption to be comparable to biological systems. And what makes a brain so energy efficient? Why can a brain deliver 38 petaflops of raw computing power with only 20 watts, whereas a machine like the Summit system at Oak Ridge needs 10 megawatts for 148 petaflops? What's the difference? And the main difference is no algorithm in the brain. And that is a hard pill to swallow for a computer scientist. I've realized during the last decades, to be honest, that computer scientists have a real problem grasping the basic idea of an analog computer, because an analog computer is not programmed by an algorithm. That's the central and most important point of an analog computer. An analog computer is programmed by interconnecting a large variety of computing elements in order to form an electrical circuit which solves some mathematical problem to be solved. Like your brain is a specific interconnection of your neurons, and your neural network just looks different from my neural network, and this combined with the synaptic weights makes you and makes me myself. So the brain is pretty much an analog computer. There's no memory, no central memory at least, and there's no algorithm which is executed in a step-by-step fashion. Brain is a brain because you have billions and billions of neurons, and these neurons are interconnected in a suitable way to yield the person you are. So what do we have? We have three classes of computers as of now. We have the well-known and ubiquitous digital stored program computers we all know and love. We have maybe quantum computers. As of now, quantum computers are still more or less creatures of a lab, and you need cooling down to 40 microkelvins and the like. So a quantum computer is nothing everyone could buy at the moment. I know there are companies like D-Wave, for example, which sell quantum computers, but these machines are still very temperamental beasts and need a lot of infrastructure for not too many so-called qubits. So if I had to guess, I would guess that a general purpose quantum computer, maybe as an extension card, as a PCI card for your server, is definitely 10 or 20 years in the future. So nothing to count on for the next couple of years. And we have analog computers. And neither of these two systems, neither analog computers nor quantum computers, will replace digital stored program computers. No way. A quantum computer and an analog computer both are pretty specialized machines. You cannot run a text processing system on an analog computer, and you cannot run it on a quantum computer. But a quantum computer may be the ideal co-processor for a classic digital computer in case you have problems which suffer from complexity problems like traveling salesman systems, cryptographic systems, and the like. And you have analog computers which are also superior to a digital computer in certain fields of applications, where quantum computers are ideal to work with problems involving computational complexities with which are non-polynomial, and analog computers ideally suited to solve problems which can be readily described with differential equations, be it ordinary differential equations or partial differential equations. So an analog computer is the ideal system to simulate dynamic systems. And the basic ideas of an analog computer are ideally suited to implement so-called artificial neural networks. If you have a look at the brain, you will realize the brain has a three-dimensional interconnect scheme that makes it fit into this pretty small skull. If you have a look at digital computers, they are basically two-dimensional interconnect systems. Why? The heat problem. You just cannot stack digital computer chips on top of each other because you cannot get rid of the excess heat of such a stack of, for example, CPU chips. I know there are stacks of chips, for example, an ARM chip with a glass so-called interposer layer, and on top of this maybe a memory chip. But if you have stacks of 2, 3, or 4 digital computer chips, that's basically all you can actually implement without running into real problems with excess heat. Given the extreme high energy efficiency of analog computers, you can at least dream of stacking analog computing chips on top of each other to form three-dimensional blocks of silicon, so to speak, which implement neural networks with a three-dimensional interconnection scheme, pretty much like in nature, with the only advantage that it runs faster than a biological neural network. If you look at one neuron, if you want clock frequency of a neuron, information is transported by a version of pulse code modulation, is in the order of a couple of kilohertz. So the switching times of a neuron are pretty long, several hundred microseconds up to several milliseconds. So if you can implement this with modern integrated circuits, but with a three-dimensional structure as you encounter in biological systems, you might be able to actually recreate systems that look and behave like a brain, only with far more processing powers. So what are the characteristics of analog computers? The first characteristic is an analog computer is extremely energy efficient. That is due to basically two facts. The first fact is there is no algorithm at all. There is no step-by-step program which has to be executed. That really saves a lot of energy. And the second trick is values are not represented as discrete sequences of bits. The idea of digital value representation is brilliant. But the problem is the faster you switch a line from one bit to another bit, the faster you toggle a line between zeros and one, the more often per time unit you have to charge or discharge a parasitic capacitor. And that's a basic problem. If you have a look at the capacitor, you all know that the capacitor looks like an open circuit for a DC voltage. But we have no DC voltages in digital computers. What we have are high and very high frequency signals, which toggle more or less in a square wave fashion between zeros and one. So you have high frequency signals which are fed into circuits which have lots and lots of parasitic capacitors, since you have interconnection lanes next to each other on a chip with only tiny isolators between them. And these, of course, form very little capacitors. And if you have to discharge and recharge a little capacitor 3 billion times a second, this little capacitor starts to look more and more like a short circuit. That is one of the main drivers of the high energy consumption of a digital computer. An analog computer, on the other hand, represents values by currents or voltages. So values are represented by continuous voltages or continuous currents. I know, as continuous as voltages and currents get. Eventually, you are down to a single electron, and that's, of course, no longer continuous, but there's still a difference between a sine wave in an analog circuit and a rectangular wave in a digital computer. So what an analog computer uses to represent values are voltages, which are well behaved, so to speak. You can always, for example, differentiate them. There are no spikes, there are no jumps, no gaps, nothing. So you will never run into the problem that you have to charge or discharge a capacitor in an instant. This, coupled with the fact that there is no central program which has to be executed in a stepwise fashion, instead, all your computing elements are cleverly interconnected with each other. This yields a very high energy efficiency of analog computers. The following number is not found in the slides, and it's currently on an informal basis only, but I'm currently working on a pharmacological research project with another university in Germany, and they have to solve a system of coupled differential equations, which we also implemented on a basically classic analog computer. And the analog computer showed an energy efficiency which is 300 to 3,000 times better than the digital machine they already used. And this energy efficiency will increase when we will be able to fabricate analog computers on a chip. As of now, all analog computers you can lay your hands on are either classic machines, which are not that energy efficient, of course, or modern machines which are still built from discrete components. So an analog computer exhibits a very high energy efficiency. An analog computer also does not suffer from Amdahl's law. Since there is no algorithm, there are no sequential parts. Like the neurons in the brain, all the computing elements in an analog computer work in a completely parallel fashion. And we should not forget that our world, the real world, where the pizza delivery boy comes from, as we all know, that the real world is basically an analog world. Everything we do at the moment with digital computers requires us to, as for example in this talk, to digitize my speech, to digitize a video signal, to process it on a digital computer, and then to retransform it into some analog signal which your ears and eyes can process. In many cases, it would be preferable if we would not have to make this double transition from the analog world into a digital world, then perform some computations and convert the result back into an analog result to hear or to see or to perform some control task or the like. So the most important things you should remember is an analog computer exhibits a high degree of parallelism. There's no program in the classical sense. It contains a lot of computing elements and no control elements at all, next to no control elements at all, maybe 1% or the like. And a program is a suitable interconnection scheme of these analog computing elements. These are two pictures from a very old book, but I think these pictures really nail it down. A digital computer can be seen as one or a couple of arithmetic logic units, the desk calculator in this picture, a large auxiliary storage, a large memory, main memory, and something which controls all of these units, the program. An analog computer, on the other hand, looks more like this. You have a plethora of independent computing elements which can implement integrations like add several values or integrate over several values. That's a very interesting point. Integration with respect to time is a basic operation for an analog computer. So a task which requires on a digital computer typically a clever integration scheme like Hoyne integration or Runge-Kutta integration is something you don't have to worry about in an analog computer. An analog computer can integrate. How does it do it? It charges a capacitor by a controlled current source, which is pretty clever. Of course, there's nothing like a free lunch, especially not in computer science. An analog computer has several drawbacks. It has very limited precision, typically 3 to 4 decimal places. And if you think of a floating point number, even a single precision floating point number has about 7 decimal places, you may think, what use at all is an analog computer if I only have 3 to 4 decimal places? The interesting thing is, the main reason for having a very high degree of numeric accuracy is that you need these accuracy for your numerical algorithms. If you integrate something, your integration scheme requires you to have guard digits and whatnot. But if you integrate by using a physical process like charging a capacitor, it turns out this limited degree of precision is typically not a problem at all. There are some problems when you need an arbitrary function, something which is trivial for a digital computer. In the simplest case, you could define any arbitrary function as a lookup table or just write a couple of lines of code and generate function values. That is something an analog computer cannot do easily, but it can do things like this. And as I already mentioned, an analog computer will not replace a digital computer, but it will complement a digital computer. And coupling an analog computer with a digital computer yields something which is known as a hybrid computer. So for me and for an increasing number of computer science, the new holy grail is a modern, highly integrated hybrid computer. A hybrid computer which has a classic stored program digital computer, which is complemented by one or many analog computers on chip, which will take over computational loads which involve solving differential equations, for example. Where are applications for this? One of the first applications that comes to mind is high-performance computing. If you have a look at typical problems which are solved on supercomputers, you find that many of these problems involve Monte Carlo simulations. There you have, of course, a linear speed up with a number of processors, since you can give one sub-problem to every processor and then parallelize with 100% parallelization. This can be easily done with analog computers as well. And most of the interesting problems in pharmacy, in weather modeling or climate modeling or hydrodynamics or whatever are based on differential equations. So most of these problems are ideally suited to be solved on an analog computer. And the idea of complementing a classic digital computer with such an analog computer is really striking. You might end up with a machine which just outperforms everything which we ever saw in computer science in problems which can be described by differential equations. Another field of application, which I already mentioned, is artificial intelligence, of course, and a very interesting field due to the very high power efficiency are medical implants. For example, a retina implant or a cochlear implant or a brain pacemaker. As of now, typical implants for medical purposes need a power source, an accumulator which has to be recharged and whatnot. Imagine an implant which requires so less energy that it can be powered from within your body, maybe with thermocouples or the like. This would really transform how we think about medical implants. Such a medical implant would become an integral part of my body. It would live with me and it would die with me. And of course, obvious things like industrial control systems and signal pre and post processing and the like. Let's have a look at some historic analog computers so that you get an impression of how an analog computer looked like and why the heck did they die out? The idea for analog computers is extremely old. The first computer known to mankind is the mechanism of Antikythera. This was found in, I think, about 1910 in a Greek shipwreck, and it was dated back to the 1st century past Christ. So that is a machine which is now 1,900 years old. And this mechanism, as it turned out after decades of research, was a full-fledged analog computer, mechanical analog computer, which solves rather intricate problems of orbital dynamics. If you are interested in this, Google for the mechanism of Antikythera. Very, very interesting. And in the 19th century and the first half of the 20th century, there were many electromechanical and purely mechanical analog computers. And beginning in the 1940s, electronic analog computers began to take over. And these electronic analog computers were leading until the late 70s, or in some areas, even the early 80s. And then they basically died out. Why? This has a couple of reasons. The first reason was that digital computers got cheaper and cheaper. And in the end, the market for digital computers was so big that the machines got so cheap that analog computers, which were still basically hand-built systems, could not compete with off-the-shelf digital computers. The next problem is a classic analog computer cannot do time sharing. So if you want to solve a problem on an analog computer, it is your machine as long as you need it. And that, of course, is not a suitable way to use a computer. And the third problem was analog computing, electronic analog computing started in the, as I already said, early 1940s. So most of the professors, most of the professionals which used analog computers were of basically equal age. And in the 70s and 80s, all of these persons retired. And the next generation of scientists and engineers and professionals, of course, had to do something different to differentiate themselves from their predecessors. Digital computers. And so analog computing died out in a couple of years. It was a real shift of paradigm. But nowadays, we are able to implement analog computers using the integrated circuitry technology we have developed for our digital machines, and thus bring back this brilliant idea of the past to the computing area of the 21st century. Let's have a look at some classic machines, and please don't laugh. It's easy to laugh about, it's so big, and it's so slow, and my iPhone can do so much more. one always has to see from when these machines are. This system, for example, is from 1960, so this was 60 years ago. And what you see here are three rather big analog computers, these double width 19-inch racks with the plethora of wires in front. And this maze of wires, this is the actual program. And you could interchange programs by removing the whole patch panel and plugging in another patch panel. And this system, it turned out after quite some research and lots of good luck, this actual system shown here was a flight simulator at the German aerospace company Bölkow, which then merged to become Messerschmitt Bölkow Blohm MBB. And this particular program seen here was the complete simulator of a vertical takeoff and landing jet fighter system. That was something that was just impossible to simulate on a digital computer well into the 1990s. And it was easily done on a machine in the 1960s. But you can also see the problems. Changing a program, even if you can just replace the patch panel, was a tedious task. You see all the potentiometers in front of the large racks of analog computers. Each of these machines had 100 potentiometers for parameters. It was a, pain the you-know-where to change all these potentiometer settings. That was a real problem, but is no longer a problem. Here you see a bit more recent system dating back to 1966. That's a medium-scale analog computer. And you see on the right side of the picture the central patch panel with a couple of cable connections which implement a simple program, and you see a row of manual control potentiometers which you can use to modify parameters in your simulation. Here you see a very interesting installation that was at the German car manufacturer Volkswagen in the 1970s. They were one of the first car manufacturers in the world who employed an hybrid computer center which ran a car simulator. They could simulate a car down to the behavior of the engine, to the gearbox, everything on a hydraulic platform. So the test engineers could take test drives in a car that was not even built yet and only existed as a bunch of mathematical equations. How do present analog computers look like? As of now, a typical modern analog computer looks like this. It got a little bit smaller, but due to the manual patch panel, you cannot shrink it down much further. Otherwise, you have real problems patching the machine, and is built on a modular basis. You see, for example, here a system which consists of 5 chassis with computing elements, and you have multipliers, you have integrators, you have summers, you have coefficient potentiometers, all the elements you find in a typical analog computer. And a machine like this can already be coupled to a digital computer, thus forming a simple hybrid computer. This circuit you can see here, which is based on an Arduino, as you have already spotted, I'm sure. This is a so-called hybrid controller card. And you see this has on the left side a front panel with according jacks where you can plug in your patch cables, and it connects to the bus system of the analog computer on the back, and it features a USB connector. So you can control the analog computer from your digital computer. You can, for example, set parameters. There are no manual potentiometers any longer. What you have are digital potentiometers. These are the 4 small integrated circuits on the 2 tiny white piggyback printed circuit cards in the middle of the picture. So you can, for the first time in decades, set up a program on an analog computer and may, for example, perform a parameter search with the attached digital computer. What are current and future developments? Of course, the next generation of analog computers must be integrated on a chip. There is no place in the 21st century for a patch panel and someone really thinking about which analog computing elements to connect to which other elements. So the first thing you could do is build something like this. This is a pretty neat little board featuring a so-called FPAA, a field programmable analog array. That is a very, very, and too simple analog computer. That's the smallish rectangular chip in the middle of the printed circuit board. And this board, for example, can be used for audio applications. If you need a filter or a simple synthesizer, you can reconfigure this tiny analog computer on a chip to perform all your signal processing in an analog way. There's no need to have an analog digital converter and a digital signal processor and a digital analog converter. No, you do everything in an analog circuit, which can be reconfigured by the attached digital controller, which is the larger rectangular chip on the right-hand side. In the year 2005, researcher Glenn Edward Cohen developed the first highly integrated analog computer on a chip. Unfortunately, this only was a research project and did not yield any commercial system, but this system demonstrated, at least back in its time, a better energy efficiency than any competing digital computer system. But this analog computer on chip, it was already reconfigurable to a certain degree, but it was suited for a very specialized problem class, a class of stochastic differential equations. So not much came from this chip. 11 years later, another student, Ningguo, wrote his dissertation on a better implementation of an analog computer on chip. And here you can see that's, of course, not a dye photograph. That's a graphic representation of the analog computer on chip. You can see how the chip contains 4 individual macro cells, and each macro cell contains several computing elements, such as 4 integrators and coefficient elements and whatever you need. There are, of course, problems. If you just had an analog computer on chip, you couldn't do very much with it. You need a specialized software stack. Hardware without software is just useless. You need a software stack and you need a hardware definition language. You need a compiler infrastructure which allows you to state your problem in more or less mathematical terms, and then derive from this mathematical description how the interconnection scheme of the analog computing elements should look like. You can download these slides after the lecture, if I understood the organizers correctly. And let's have a very short look at typical computing elements and examples. Let's jump right into a differential equation. That's maybe a little bit too mathematical, but it's a pretty simple problem. Assume you have a differential equation like the one stated in 1. You have a variable y, which represents an unknown function, and all you know is that the second derivative of y dot dot, plus omega squared times y equals 0. And the question is, which functions solve this equation? Of course, the 0 function is a solution, and sine would be a solution, and cosine would be a solution. But how would one program something like this on an analog computer? On a digital computer, you need a mathematical package and integration routines and whatnot. On an analog computer, the idea is pretty simple. Have a look at the circuit shown on the bottom of this page. This funny triangular shape with the attached rectangular shape is an integrator. And whatever you feed into the integrator, you get at the output of the integrator as its time integral. There's a sign inversion, but you can ignore this for now. So if you assume you knew what y dot dot is, which you do not know, but just assume you know what y dot dot is. You could think about, okay, I feed my function y dot dot, which is represented by a time varying voltage, into this integrator. And at the output, I get the function minus, due to technical reasons, y dot. This is fed into another integrator yielding y, and feeding this into an inverter yields minus y. And if you rearrange this equation number 1, you could subtract the omega squared times y and get y dot dot equal minus omega squared times y. And now let's assume that omega is just 1. So this equation would simplify to y dot dot equals minus y. And that's exactly what we have just plugged together from 2 integrators and an inverter. We fed in an unknown function y dot dot and got out an equally unknown function minus y. But according to the equation, these two functions are the same. So I can plug the output of this inverter into the input of my first integrator, and voila, I have a loop of computing elements which implements a mathematical equation, a differential equation. And if you feed this with the circular shapes are potentiometers, if you feed the integrators with suitable initial conditions, you really get at the output, for example, a sine wave or a linear combination of some sine or cosine functions. And that's really mind-blowing. There is no algorithm at all. You only need the mathematical description and then derive a setup of computing elements from this mathematical description, feed it with initial conditions, and you get out as a result a time-varying voltage, which is your unknown function you are looking for. And in a hybrid computer, you could now digitize this and feed this to the digital computer, which could then either apply some clever numerical algorithms or just plot a function graph or the like. And if you have a look at the slides later on, you will find two more complex examples, a van der Pol oscillator and even a partial differential equation, which can be also readily solved with an analog computer. And you see that is a more realistic program, which requires dozens of computing elements. Nowadays, with the possibility of a highly integrated analog computer on a chip, it is very possible to think about computer setups which do not require dozens or hundreds of computing elements, but thousands of computing elements. We are currently working on an analog computer on chip. We already had meetings with a customer, and we have one potential customer who dreams of, and I'm not exaggerating, who dreams of 10 to the power of 7 to 10 to the power of 8 integrators. They think about 100 million computing elements cleverly interconnected to solve some very, very hard problems. At the moment, they rent computing time on a supercomputer installation, but that is still too slow for their actual problem. And their only chance in the next couple of years to solve their problems in ideally real time is to implement a very, very large, highly integrated analog computer. So you see, we have three computing paradigms: the classic digital machine, the quantum computer, which is still far in the future, and the analog computer, which is something which could be a reality in the next 1, 2, or 5 years, maybe. So now I'm at the end of this little talk. Thank you very much for your interest, and I'm open for your questions if you have any questions. Any questions, anyone? Okay.
Okay. Hello. Okay, hello. So also from my side, thank you for this lecture, Professor Ullmann.
You're welcome.
It was quite informative. And now we have the opportunity to ask you some questions. And also all of our viewers have the opportunity to ask questions via Live Ask. And I can pose them to you. So the first question I got was for the non-math students out there. Could you describe what is an attractor and maybe name a use case for its computation?
Okay, an attractor is a structure to which a function is drawn to from Latin attrahere, if I remember correctly. If you have a time-varying function, an attractor occurs in dynamic systems. And in a dynamic system, you are interested in how, for example, a pandemic or an epidemic or something evolves over time. And what you typically do to visualize or represent a system like this is you make a so-called phase space plot. Let's think about the COVID pandemic. If you have a look at it from a mathematical point of view, you have 4 so-called coupled differential equations. You have one equation describing how people get infected. People get infected by meeting other people who are infected. And you have another equation describing how an infected person gets a sick person. And you have a third equation describing how a sick person is removed from the sick persons either by recovering or dying. And what you are now interested in is how do these 3 variables, how are they interconnected? And you can, for example, draw a graph showing on a 3-dimensional graph, and on each axis you have, for example, the number of infected people, the number of sick people, and the number of recovered people. And what you get is a curve in a 3-dimensional space, which describes the time-depending behavior of your overall system. And an attractor is a graph to which such systems are drawn to, so to say. So an attractor is the description of such a system in phase space when it became a stable system. It can, for example, go into an oscillation, and you will always, for example, typical influenza or some simple infection, which you will get every winter. Every winter you get sick, then you recover, and next winter you get sick again. So you have something which would look like a circle or an ellipse in the phase space, and this ellipse would be the attractor of the system.
Okay, thank you very much. That was a really good explanation. I understood it very well. Let's come back to your fascination for analog computers. I'm quite a bit interested in how did that start? When did you first get interested in the analog world? Because most of computer science, which is taught here, is completely of the digital computing world. So what was the Startfunken, we say in German, for your fascination?
It started in my teens. So in the first half of the 1980s, I found a book on analog computing in the library of our school. And I didn't understand a word of this book, and this got me eventually into mathematics. But what I understood was that this was a way to solve problems without having to bridge the gap between the mathematical description and the actual implementation by an algorithm. And it never ceases to fascinate me that you can have a problem and a solution and do not need to bridge this gap by an algorithm. It's so much simpler than a digital computer.
And have you ever owned an analog computer, or what was the first one, if you have owned multiple, that you owned?
Yes, I own a lot of analog computers, and honestly, if anyone is interested to come for a visit, if you are near the Rhine-Main area, near Wiesbaden, feel cordially invited to visit us. This is honestly the world's biggest collection of analog computers. So my wife and I, we have collected really about 100 analog computers as of now. And my first analog computer was a homebrew analog computer, which I built, I think, 1984 or the like, from simple operational amplifiers, capacitors, and resistors. And this really, this spark never ceased to, I never lost interest in this really great way of performing computations. It's so simple to build an analog computer. If any of you ever built a digital computer, and I mean not with an FPGA, that's cheating, describing a digital computer in VHDL and just flashing it on an FPGA. But if you really built a digital computer with single TTL gates, which I did twice in my life, you know how hard it is to even build a simple digital computer. Building a simple analog computer is just that simple. You can build an analog computer in 1 or 2 hours of time if you have some resistors, capacitors, potentiometers, and operational amplifiers, and you can readily solve differential equations. It's really unbelievable.
Yeah, that's quite interesting. The only analog computers I knew from my own life are some synthesizers for the music production. So,
yes, for example, that's a good example.
Yeah, which are simple to operate
yes.
very easily, but quite effective. Yeah.
Yes.
And what would you consider that to be one of the first real use cases for an analog computer?
No, the first real use cases were, and I think most of you already guessed it, were military use cases. The really first electronic analog computer was the onboard control system of the V2 rocket. And this evolved into the onboard computer system of the Redstone rockets at the Americans. And the Russian Proton rockets, for example, flew, I think, until about 10 years ago with an analog control system, like in the 1940s, 1950s. And apart from military applications, the earliest other applications were aerospace problems, simulating airplanes, simulating spacecraft, simulating cars, and simulating chemical processes. Chemical industry was a very big user of analog computers, especially petrochemical companies. It's very difficult to, for example, build a rectification column if you have to build a distillation system, which is 120 meters high, and you have a heater with 100 megawatts. Where do you place your feeds and all your ducts and tubes? That's really hard to solve, impossible to solve manually, but it's readily described by partial differential equations. So industrial applications like these also made large use of analog computers.
Okay, and when we look at today, what are the analog computers used for today? Because I could imagine that in the military sector, they all switched by now to digital computers, and also in the production way, like the chemical industry. Now I think it's more efficient to do that.
Definitely. As of now, analog computers have mostly died out. But if you have an analog computer on chip, that would be a really disruptive technology. Think of medical implants, think of high-performance computers. And what we are currently doing, and we is 3 friends of mine and I, we are currently working on an analog computer on chip as a technology demonstrator, which we will use to build the world's first fully reconfigurable analog hybrid system for higher performance computing problems, for example. So as of now, there are no analog computers except for some institutes which build their own machines or which bought a new system. But apart from these, there are no analog computers out there in the wild.
Okay. And when we look kind of in the now artificial intelligence world, when we look at these artificial neural networks, you kind of talked about that in your lecture. When do you believe the vertical stacking of analog computers will be possible in a research environment? And do you think that this will solve current problems that we suffer from with artificial neural networks because of the way analog computing is working?
Analog computers for artificial neural networks were, for example, already used in the Human Brain Project you may have heard about. But the Human Brain Project, they used a technology called full wafer scale technology. They used a full 30-centimeter wafer and implemented millions and billions of synaptic elements on these wafers. But the main problem still was it's a 2-dimensional interconnection scheme. If I had to guess, I would say that we will see the first 3D stacks of analog computer chips in about 5 years. It's basically all the ingredients for this technology are readily available. What we need are suitable analog computer chips for neural networks and suitable interposers and manufacturing technologies to build stacks consisting of more than 2 to 4 chips as is currently possible. I am not sure if an analog implementation of a neural network will exhibit a basically different behavior than a digital implementation, but it will be smaller, will require less energy, and will be thus I'm pretty sure will exhibit also a higher performance than a classical digital implementation of an artificial neural network.
Okay, that's quite interesting. We have another question coming live via Live Ask. What resources do you recommend for getting into analog computers?
Sorry, that's a shameless plug for my own website. I would suggest have a look at the analogmuseum.org webpage. There's an introductory section and a library section with literally hundreds of scanned books and articles, all dealing with analog computing. So the most comprehensive collection of analog computing information can be found at the analogmuseum.org webpage. And there are, of course, I have not prepared this, but I was reading corrections. Oh, that's now a little bit difficult. Okay, there are books on this topic on the market by De Gruyter, for example. This one here, Analog and Hybrid Computer Programming, which gives a good introduction and contains a wealth of worked examples. So you can even, if you build your own little analog computer or come for a visit and play with a real analog computer, you can already use programs from this book, for example.
Yeah, that's quite interesting. And I think we will be able to publish this link for the one who asked the question. Mm-hmm. Now, to come to a little bit of a final, we will see you again on Friday. And I would like to know, what topic do you have planned for Friday? What can we look forward to?
I'm still open for suggestions, so to speak. So I'm completely flexible. The idea was that we would basically cover the same topic, but if there's interest on any other topic, just let me know.
Okay, so thank you very much for coming today.
Thank you very much.
And for giving this lecture. It was very informative and I really enjoyed it. And now I think we will switch over to the Orga team.
Thank you very much. Bye, everyone.
Goodbye, who make the final.